If you've taken an introductory statistics course before, you know that hypothesis tests are often used to determine if there's a difference between two groups or a difference between two treatments. For example, let's say you need to buy batteries for your gaming system. Do generic or brand name batteries tend to last longer? In other words, if brand name batteries last longer, maybe they're worth the extra money. Some people are interested in environmental issues. For example, when testing water quality, do the pesticide levels in a river depend on whether you take the water samples near the surface or near the bottom of the river? In education, are certain types of learning strategies better than others in increasing memory skills? In business, you may have two different pricing strategies, a higher cost or a lower cost. Does the price of a cup of coffee influence sales at your coffee shop? In agriculture, does adding additional nutrients to the soil change the yield of a particular crop? Or in medicine, which medication is most effective in stopping a disease? In introductory statistics courses, you are typically shown how to conduct a two-sample test to compare two group means. For example, in our textbook schistosomiasis study, we want to know if a new drug will reduce the number of parasites existing in the liver of a sample of lab mice. In order to do a two-sample t-test, you first develop a null and alternative hypothesis. In this schistosomiasis study, we first write the null hypothesis, which says the treatment has no effect on the number of parasites. We often write that H0, the mean of the control, is equal to the mean of the treatment. The alternative hypothesis, our research hypothesis, what we hope to prove, is that the treatment reduces the number of parasites existing in the liver. In other words, H1, sometimes written HA, is that the mean of the control is greater than the mean of the treatment. Once we state our null and alternative hypothesis, we get a sample of mice. We randomly assign mice to the treatment and the control, conduct the study, and gather data. We calculate summary statistics, such as the sample mean, the sample standard deviation of each group, and then we use those sample statistics to calculate a test statistic. In this example, we find the t-statistic to be 2.92. We then compare this test statistic to the theoretical t-distribution. So where does 2.92 fall in the t-distribution? We see that the probability of observing anything greater than 2.92 is only 1.1%, or 0.011. In this example, a p-value of 0.01 is relatively small, so we would tend to reject the null in favor of the alternative and conclude that the treatment does reduce the number of parasites in the liver. However, we have to be very careful not to trust a p-value provided by statistical software or a table unless you are certain that appropriate assumptions are met. Hypothesis tests that involve theoretical distributions, such as the normal distribution or the t-distribution, are called parametric tests, meaning that they are testing a parameter, such as the mean, from a specific distribution. These hypothesis tests work well as long as several assumptions are met. For example, we assume that we have independent and identically distributed samples. We also assume that the data follows the normal distribution, or that we have a large enough sample size to ensure that the sample means are normally distributed. In this study, note that we only have 5 observations in each group. This is not enough to be confident that the sample means are truly normally distributed. Since we cannot be confident that the sample averages are normally distributed, we should use a distribution-free test, also called a nonparametric test. Such tests do not require the distribution of our sample statistics to have any specific form. Instead, they are based on computer simulations. Nonparametric tests, such as the randomization test we're going to talk about in this chapter, is particularly useful when the sample data is skewed or when the sample size is small. In addition, nonparametric tests have the advantage that they're not restricted in the parameters we test. In introductory statistics classes, almost all the hypothesis tests that you conducted were based on the mean, but nonparametric tests can be extended to other parameters of interest, such as the median. In this chapter, we will show that the randomization test estimates the p-value to be about 0.028, which is quite a bit different than the 0.011. We will also show that in this study, the randomization test provides a much better estimate of the exact p-value than the two-sample t-test. In 1935, R.A. Fisher, perhaps the preeminent statistician of the 20th century, introduced the randomization test in his famous book, Design of Experiments. At that time, he acknowledged that the randomization test was not practical because of the computational intensity of the calculations. Clearly, 1935 predates modern computing, where we could use computers to create simulation studies. Fisher went on to assert that the classical two-sample t-test was a good approximation for the randomization test when sample sizes are large enough. We are fortunate that, in this age of modern computing, we no longer have to routinely compromise by using a two-sample t-test as an approximation of the randomization test. One other important note. It's important to recognize that nonparametric tests can be used in any situation where parametric tests can be used. In summary, randomization tests have very similar goals to the traditional two-sample t-test. In parametric tests, we calculate sample statistics as estimate of the corresponding population parameters and then calculate a test statistic, such as the t-statistic, and then we compare that t-statistic to a theoretical distribution. We reject the null hypothesis if our test statistic is extreme relative to the table distribution. Randomization tests differ from parametric tests. While both procedures, parametric and nonparametric tests, calculate some sort of test statistics, the nonparametric tests, such as the randomization test, do not compare statistics to table distributions. Instead, we compare our statistic to the results we obtain when we repeatedly randomize the data across groups over and over again. The idea of randomization tests date back to 1935, but the application of such techniques had to wait until computers came along. As we continue to go through this chapter, I hope that you will see how the randomization test has many benefits over the parametric tests you typically saw in your introductory statistics class.